So we can hand on now to Maggie, who's going to talk to her about, machine learning and her project.
So I'm Maggie Lieu. I'm a research fellow in Machine Learning and Cosmology at the University of Nottingham. And I think this talk is going to be a little bit different from what has been said so far, which is more like using AI to enhance your kind of teaching, whereas this is more application focused. The main part of my talk is going to be about a master's program that we run called Machine Learning in Science. And this is what funds my research fellowship. So I am 70% research and 30% teaching. And as a background, I'm an astrophysicist. So you'll see some of my research in this talk. It's going to be split into kind of two parts. At the start, I'm going to talk about the master's program itself. And then the second part, more about kind of projects, not just within the master's program I've done with the students, but also like for the master's students that I've supervised previously. But before I start, I probably should thank Jez for inviting me to speak here and all the Zuniverse. So thank you. So we've had a lot of like buzzwords thrown around, and I'm really surprised that no one's mentioned it, like AI, machine learning, and deep learning. What's the difference between all of those? No one said that. Just used it absentmindedly. Artificial intelligence generally means kind of mimicking human behavior in general. Machine learning is a very kind of subset of AI, where you're dealing with data and using algorithms to infer information and patterns from that data. And actually, my talk is going to be focused on machine learning rather than AI as a whole, and in specifically deep learning, which is a further subset of machine learning, where you're working with algorithms that are much more complex with deeper neural layers. So why do we want to use machine learning? So first of all, processing large data sets. One of the missions that I've been working on is maybe you heard of the space mission that was launched on the weekend, on Saturday, Euclid. It's a space telescope going up to space to measure images of galaxies, billions of them, and it's going to be generating 100 gigabytes of data to download every single day. Over the course of 6 years, there's going to be hundreds of petabytes of data to process altogether. So if we want to process them in traditional methods, it's not going to be possible. We need machine learning methods to deal with this in an automated manner. Identifying patterns, like I said, space and astronomy, we're processing so much data. Sometimes we're going to be having to look for patterns in tens, hundreds, even thousands of dimensions. Machine learning can do this much better than us humans can. Making predictions. Machine learning can help us with planning activities, predicting weather on different planets and the climates, predicting events in astronomy, and also automating tasks. So a lot of the traditional astronomy methods, we have to look at things by eye. We don't have tons of data to work with, but if we can automate these things when we're dealing with the hundreds of petabytes of data that we'll see with Euclid, we can do it with machine learning and save us a lot of time, so we can focus our efforts on being more creative and doing the actual science rather than the data crunching. So machine learning and science, the program is a 12-month taught master's program, and it's very applications and project focused. Our students do a lot of research during this master's. It's cross-faculty, so it runs via physics and astronomy, which is what I'm part of, but there are modules taught by computer science, mathematics, and neuroscience, and we get students from across these kind of backgrounds and more. So our applications are everything from like medical imaging to traffic processing, working with helicopters, for example, in the defense industry, lots of different kind of research areas there. Student to stats, you can see that we started this master's in 2019. There was only about 12 students then, and it's actually growing exponentially. So you can see across the board, there are more students that are interested in using AI, specifically with a focus on science. And we, as far as I know, we're the only university that offers this kind of science-focused application for machine learning. One of the problems that has been noted to me actually is that I think on the outside ring is nationalities based on 2019. So 66% UK students and the remaining over international and EU. Obviously, more recently after Brexit, our EU students also become international. So actually now 70% of our students are international. And this is a huge problem because if we want AI, if we want the UK to be a powerhouse in AI, like the government has said, then we need to keep that kind of knowledge in-house. But it seems like, I don't know, well, we're attracting more international students, and I don't know what the solution is.
I'm just going to ask, does that mean that the total number for between 2019 and 2022, you basically have about the same total amount of UK students? So of that, because they're a larger fraction of that smaller number, does that mean you have about the same amount that are coming through? So the interest in UK students is not increasing.
Yeah, I guess so.
That's interesting. Despite the awareness, general awareness of AI has really gone up. I mean, that includes the UK.
Absolutely.
They're not interested in doing this. That's very annoying.
I don't know what the answer is. Yeah, and that's something that we're talking with our marketing team to try and focus on attracting more UK students to the course. These are the modules that we teach: Machine Learning in Science 1 and 2, Statistical Foundations and Statistical Machine Learning. I don't know across how you've been teaching, but like over the years, we've been seeing like students become less and less knowledgeable in basic maths, and it's been a huge problem for us that we're actually incorporating more maths into our modules. Some excuses for that is like a lot of our students have years out, which is fine, but other students I'm not sure. We have biology students, neuroscientists, so psychologists. I know those students won't do a lot of maths, so some are coming into a machine learning masters without any like even A-level maths. So that's some big problem there, like students that have just done GCSE maths and then coming into masters to do machine learning, and maths is a core module to understand machine learning really. Scientific programming in Python, ethics, big data, cloud computing, quantum computing, designing intelligent agents, computational neuroscience and computer vision. So specifically, I teach machine learning in Science 2, and I'm involved in the scientific programming in Python. So that's what I'm going to talk more on, the machine learning in Science 2, which is very focused on deep learning. Three of the kind of main areas that this module incorporates is time series analysis. So in Astro data sets, we have light curves, so variable stars, where we're using methods like recurrent neural networks to process this kind of fluctuant time-based data. A lot of stuff on computer vision. So obviously astronomy, stars, even Earth observation, we're looking at imagery data in general. So computer vision is super important. And then also transfer learning, where we're taking information and models that are trained for one application and kind of repurposing it for another application in our methods. Actually, all these three images are generated from Bing Image Creator, which is a free image kind of AI model. If any of you haven't been using that already, you should. One that I didn't mention is also reinforcement learning we teach in this module as well, which is using like feedback mechanisms with rewards and agents to kind of improve your model over time. So in addition to the lectures that we teach in our module, every week we have workshops where the students will have hands-on programming of machine learning algorithms and stuff. One of the tools that we use is Google Colab, which is a free resource, and I think it's really helpful in teaching machine learning, especially if the students don't have access to GPUs, so graphic processing units, which are definitely needed if you want to train any sort of machine learning model. They also have TPUs free of charge, which is kind of a step up tensor processing units. In our in-house at Nottingham, we do have several GPUs, but obviously with so many students, they quite quickly get used up and students are fighting over for it. So it's really great to be able to have such a great resource. Yeah, so it's really great because you can do programming inside of it. It's got Python, it's got R if you code in R, and all of like the main libraries are already installed, so you don't have to faff around with like pip installing different packages as you need. So I think all that's great, and you can also use it in collaboration with like other students if you're working in teams. It's kind of like Google Docs. You can see everyone typing at the same time, and loads of people can edit the same file online. So I think that's a really great resource to have. So at the end of the project, we make the students kind of program this self-driving car. So this is a Raspberry Pi 3 based car, full model. It's got a camera equipped, and we developed an API where students can get their phones or laptops and drive the car around different tracks and stuff and collect their own data, because obviously having data is important for training your models. And the purpose of it is afterwards they would train a machine learning algorithm to navigate around different tracks, like an oval track, figure of 8, T-junction, avoiding obstacles like pedestrians and trees, and ignoring them if they're on the side of the road, obviously, being able to turn left and right, being able to stop at traffic lights or go when the traffic light is green, and all sorts of maneuvers like this. And it turns out that this is actually quite a challenging problem, because obviously you've got the different lighting and different environments that the car is in. Also being able to train a model that's fast enough to react, because if you're not reacting in time, if you're not turning in time, then you'll miss your junction or whatever. So it is actually quite a difficult task to do, but quite a fun one that the students really enjoy. We still ran the project when it was COVID, but the students weren't allowed on site to do these training things. So you can see this application in the case of, like, for example, Mars rovers, where it's really important to have automated systems for like landing spacecraft or driving your Martian rovers, because there is this latency between Mars, 6 to 20 minutes, depending on where Mars is. So if you had machine learning algorithms built into these systems, then you could be able to more efficiently kind of navigate obstacles and problems that arrive in real time. I don't know if you guys watched like the iSpace landing. It was, I think it was 2 months ago or something, and it crashed because they trained it on a simulation that didn't even take into account the crater. So it detected the edge of the crater and it thought it was close to the ground and kind of landed a bit too early. So collecting data is important and using knowledge. But in addition to live testing, we also allow the students to make models that are more adapted to non-realistic, non-live scenarios, so they can make the most complex models that are most accurate as they like. Obviously, these wouldn't work in real life because they would be really slow with the kind of hardware that they're limited to. But we use this platform called Caddle, which is also really useful for machine learning problems. You can build a classroom there where you can upload your own data and allow students to kind of compete to solve this problem. And you'll see that there are a lot of industry that post their data sets and problems up there for people to play this competition and win real like monetary prizes, which is a great learning kind of place if you want to start in playing around with. Okay, so applications. One of the applications in machine learning is detecting asteroids. This is kind of the first project that I worked on using machine learning, actually. And originally I wasn't interested in asteroids at all, and generally astrophysicists aren't. I'm actually interested in weak gravitational lensing. So this is the distortion of galaxies due to the presence of gravity and mass, in particular huge galaxy clusters like this one. You can see a big arc there of a galaxy, and this is distortion due to the mass of the galaxy cluster. But in general, a lot of these galaxies will have distortions in them that you can't see unless you statistically average over hundreds of thousands of them, and you'll be able to kind of sense the presence of dark matter here. And that's the purpose of Euclid that flew on Saturday. This is what Euclid's War data will look like. And so you can see it's actually a huge mess. You've got like cosmic rays, you've got bleeding, you've got what we call ghosts, which are kind of reflections of the stars here. We're interested in galaxies whose shapes have been distorted by less than a fraction of a percentage. And so I don't know about you, but for me, it would be impossible to figure out where are galaxies here, which ones are distorted. A lot of these here are also asteroids, which are slow moving on the sky, and they appear to be like distorted galaxies. And so that was how that project arose. And using machine learning, we could get like 98% accuracy on classifying all these different objects, asteroids, galaxies, cosmic rays, stars. So it was pretty amazing, especially given the amount of data I said Euclid will be collecting, like over 100 gigabytes per day. One of my students, well, one of my first master's students, when I was at the European Space Agency, helped use machine learning to classify galaxies in X-ray and optical data. So typically in X-rays is how we detect galaxy clusters. And we'll have a very basic algorithm, wavelet filtering, apply kind of a Gaussian filter over an image to search for these blobs. And then humans, by eye, will cross-match with the optical data. Is there a cluster of galaxies there? If so, it's probably a galaxy cluster. If not, then it's probably an AGN. And this was fine when we were working with Exmem and Chandra, when maybe we would get, I don't know, 200 galaxies, 300 galaxies to look through. But with eRosita and Euclid, we'll be getting tens of thousands of galaxy clusters. And in that sense, it's no longer going to be feasible to do this by hand anymore. And so Mate, who is now doing a PhD at the University of Turin, developed this Zuniverse project. For those of you who are not familiar, Zuniverse is a crowdsourcing project where you can create a project to enlist the help of the general public to help you collect data. And that's what we did. We kind of had this small set of, I think, 300 galaxy clusters. We knew the ground truth, but we wanted to know how well the general public would be able to help pick out these galaxy clusters. And based on that, we could extend it to even more galaxy clusters and allow the general public to help us collect more data so that we could have enough for a machine learning algorithm to train on. This is what we call a ROC curve, and some of the results from what he found that we published in 2020. Two models here, convolutional neural network and a transfer learning model that I said previously. If we train a model on something else, like cats and dogs, we could repurpose it for use here to distinguish galaxy clusters from non-galaxy clusters. And with his model, the best model was getting like 96% accuracy, so that's really well. This dashed line is what we would expect if we were doing as well as chance. So you can see most of the models are up there doing much better than chance and much better than what we could do as humans by eye, actually. This is a beautiful galaxy cluster. Westerland 2, that I love seeing. It's from the Hubble Space Telescope. Actually, the Hubble Space Telescope images never look as pretty as that when it's actually collected. I had a student called Antonia Wojtkova, and in 2021 we published her research where we were using machine learning, AstroUnit, to take short exposure images and kind of try to replicate long exposure images. So taking a kind of, I think, 50-second image on the sky and projecting it to what we would expect to see from 100 seconds and trying to maintain the signal to noise ratio. And this was super important to us because the Hubble oversubscription rate is 6-to-1. So that means for every 6 researchers asking for time on the Hubble Space Telescope, only 1 would get it. And Hubble is extremely expensive to run. It costs 100 million just to keep the Hubble in space per year. So using machine learning, if we could maximize the efficiency and information gain from the data that we collect, turns out it's unbiased in flux and size, which is what's important for me, for the galaxy shapes, for gravitational lensing and dark matter detection, then that's great. And that's what we found from her research. Similarly, Sam Swear, doing a similar thing with short exposure images, trying to reproduce long exposure images, but this time in X-ray telescopes. X-rays is a bit more challenging because they're Poisson-based, so we're getting much less photons on our detector, but it is possible to do. And in this case as well, we're looking at denoising images. We can figure out kind of like points of interest that we can go back and with other telescopes for further kind of analysis if we want to follow up on that. The other thing that Sam did in his paper was to see if we can do super resolution, so training on a low resolution image of XMEM, upscaling to a higher resolution of Chandra Space Telescope, and it seemed it was possible. Last year I ran a project working with the Rights Lab at the University of Nottingham to detect slavery from space, in particular working to look for these brick kilns across India. It turns out like 90% of the factories host slavery, a lot of them child labor, child slavery. And it's working with the UN because the UN would follow up and go into these brick kilns to kind of figure out, are they exploiting their workers in there? So this is based on planet data from space, and these brick kilns have very specific shapes, and we were trying to see if we could use low-res imagery to pick out where these brick kilns are. And traditional methods would use higher resolution images, and they were kind of several different algorithms, first to figure out where a region would have a potential brick kiln, and then another algorithm to classify, is it really a brick kiln? But Albert, who is now doing a PhD in the Rights Lab at Nottingham, was able to kind of do this kind of end-to-end model to pick out exactly where these brick kilns are in these images. And then lastly, the project I've got running now with 3 students, Dongzhang Qi Kao and Ruqing Meng, is about space worms. In 2021, Nottingham launched a bunch of worms, C. elegans, like this one, into space to study muscle effects on astronauts. Traditionally, the researchers that look at these worms would have to analyze it with tools like Fiji, where they would have to manually extract the lengths and widths of the worms. So you'd have to put little points and be like, okay, this is where the worm is, and then extract a length and calibrate it to this kind of bar. And this is still ongoing research, but the idea is that they want to be able to pick out exactly where these worms are, be able to pick out their lengths and widths, and then figure out what the effects of microgravity are on these worms over time. Turns out this is really difficult because over the course of 2 weeks, which is a typical lifespan of these worms, they will multiply. So I think on this Petri dish, originally they had 20 worms, and at the end of it, you have hundreds or more worms. It turns out it's a difficult problem to do, keeping track of a single worm over time. Earlier, someone mentioned about having data sets, so that this is just one I wanted to throw in. I created this GitHub where we store some kind of data sets based on space, one with the cluster classification in X-rays and optical, I talked about in Matei's paper, and also galaxy MNIST, so those familiar with the MNIST data set of numbers that typically people use to train models. We have a galaxy version of that, and I put it on this GitHub that we use to teach our students, and I'm hoping to add more data sets to that over time. Eventually it is open to use, so feel free to use it, and it's like a TensorFlow data set, which is quite easy to use if you use TensorFlow. You use it in the same way, essentially. So in summary, there are loads of applications of AI in space and astronomy. It makes for easy and fun projects to enhance learning. Hopefully I can take something away from that. Thanks.
So we've heard from Mike earlier about the problems of data projects and how 50% of them fail. How do you tackle that?
How do I tackle data projects failing? Well, usually I have a good intuition of whether they work or not, but there's another problem of whether the students are able to get the project done. And actually recently with this worm detection, I had a bit of a panic attack because the students were like, we don't have enough data, it's not working, it's not working. And I was really worried. They went back to the lab, collected more data, came back, still their models weren't working. And then I just kind of did it myself in an hour, and I was able to get really nice results. So I was just like, it does work, just keep at it. But I think with these projects, they're generally quite simple problems, and we know exactly what the problem is, whereas Mike was talking about, in those cases, you don't know really what your problem is. You're asking for something that you don't actually want, whereas here we set it ourselves.